And with that, I'll just go ahead and jump into our first talk with Christian Steinmetz. And we're very happy to have Christian here. He's a PhD student working within the Center for Digital Music at Queen Mary, University of London. And he researches applications of machine learning and audio with a focus on differential signal processing. He's also been an intern previously with Adobe, Meta AI, Dolby, Bose, Tape-It, and Cirrus Logic. And he's here to talk about neural audio effects. And with that, take it away, Christian. And for anybody in the chat that wants to ask questions, please feel free to ask questions. We welcome those, no matter how, no matter what experience level you may be at. And just please precede those with the word question so I can identify those and make sure that we record them. So take it away, Christian.
Yeah, thanks so much for having me. It's super exciting to be here, actually giving my second talk at the Audio Programmer Meetup. I spoke maybe a year or two ago as well. But as Josh said, I'm a PhD student at Queen Mary, University of London in my second year, about to start my third year of the PhD. And I'm kind of researching applications of AI and machine learning in audio, specifically in the context of audio engineering. And today I want to talk to you about just a piece of our research, which is focused on this idea of neural audio effects. And there are some kind of, there's obviously a lot of technical details in some of these works, but I actually want to kind of try to give you a high level overview and kind of the biggest take home insights from a lot of our work. So as I'm sure many in the audience are very familiar with, audio effects are a super important tool in the audio production process across all different types of areas of audio production, whether it be music or also film, game sound, and other things. And there's kind of a long and rich history also of audio effects, all the way from our first analog audio circuits that ended up being put into boxes and used by audio engineers to kind of our modern day plugins that are many of them digital recreations of analog, as well as kind of new digital inventions as well. And I can't really stress enough the importance that these kind of devices play in the process of audio engineering. And so kind of to kind of frame our discussion today, I kind of just want to talk a little bit about a history of audio effects at a very, very high level, kind of to show where we're thinking and the future of audio effects may go. So in the past, we can see that like a lot of analog audio effects and audio tools kind of defined how people created music, and still is the case today. Something like the mixing consoles from Abbey Road Studio from the 50s that kind of like defined how people could now deal with multi-track audio in the recording studio with bands like the Beatles and things like that. And then we had things like the LA2A compressor in the 60s that kind of, was now giving audio engineers the ability to control dynamics of the signal, which was a huge, breakthrough. Before that, there was no way to really control the dynamics of your recording as much. And then we had things like in the 70s with researchers and audio engineers like George Massenburg and others that were working on this idea of the parametric EQ, where like, can I have a filter where I can vary the cutoff frequency and kind of have this like super precision? And you can kind of see like as the development of these analog effects was happening, there was kind of like this idea of giving more power to the audio engineer to manipulate sound. And when we look to the present, I think the biggest defining factor in my mind is the fact that all of these tools have been put into your laptop more or less, right? And now they're kind of available to everybody or a lot of people in some sense. And you can kind of have now hundreds of instances of these effects that used to be giant pieces of equipment that were very expensive. And I think that's been great for the development of the field of audio engineering. And I think it's not just this democratization, but also there's kind of been enabled new types of effects that weren't possible before. Something like Fab Filter, which is like this amazing EQ that gives you all of these powerful controls, that wasn't really possible in the analog domain, or things like Auto-Tune that, have also kind of defined some areas of audio engineering, which again, like was facilitated by essentially kind of having DSP and using that as a framework for developing audio tools. But for us in the research field, we kind of say, well, what is the future going to look like? Where are we going on this path of audio effects and audio engineering? And that's kind of what I want to discuss, just one component of where this future might be. And that's kind of part of what our research is interested in. So to frame our discussion, I think we need to talk somewhat formally about what an audio effect is. And here is kind of just like the most simple, basic block diagram. You could think of an audio effect where you have some audio that you put into this box. It does something inside that box and gives you some kind of modified version of it. And it usually has some control parameters that the user are exposed to the user that they can kind of change the behavior of this box. And I realize this is a super general definition of an audio effect, but I think from a practical sense, it makes a lot of sense for the audio engineer's perspective, right? Because they just kind of view it as a box and they can turn the knobs and see what happens. And obviously having a deeper understanding of what's inside the box can be useful, but it's not strictly required to use it, right? And so I think this kind of sets up that this is actually a very broad thing that we can think about. And so to introduce neural audio effects, it's really just a simple extension of audio effects in which it just requires that inside this box, there is a neural network or some machine learning kind of approach happening inside there. And that kind of gives us this new type of class of effects that is actually kind of a subset of all audio effects, right? But they still kind of do the same thing. We put audio in, we get audio out, and generally have some kind of control parameters. And as far as applications go for neural audio effects, like why would we want to put a neural network inside of a plugin? It is a great question. And I would say the predominant application thus far has proven to be analog emulations or virtual analog. So instead of having to kind of build complex models, digital models of the circuitry inside these kind of classic analog boxes, a lot of people in the research field have shown, and now in some products, that you can actually build a neural network that learns to emulate the behavior of some analog device just by measuring the audio that goes in and out of that box. And I think this has been really successful in the last 5 years or so in machine learning. But there are other applications as well, something like differentiable audio effect proxies, where you kind of train a neural network to emulate effect so that you can actually use it to have a neural network that learns to control that effect. And that was some previous work that we had done, basically trying to build intelligent systems that control audio effects. I won't talk about that today, but I just wanted to bring it up as an application. I think what's also interesting is that my definition of audio effects kind of also covers these other tasks in the research field that don't generally get connected with audio effects, like things like source separation or speech enhancement and denoising. Again, I don't think we're going to talk about those today, but they can kind of be fit into this framework of audio effects. And finally, the main topic that I want to discuss today is about using neural audio effects to perform audio effect design, particularly to design new audio effects. So instead of emulating existing effects, how can we use these approaches to actually create novel audio effects? And so hopefully that gives you some kind of framing for what I plan to talk about today. But before we get into too many technical details, I also want to bring up some important questions in audio effect philosophy as I think about it, which are kind of even higher level questions than what I was just discussing. One question, like why do we use audio effects, and how can that inform our design of audio effects? And assuming that we know we want audio effects, how is the current process of designing these, right? How does it actually go from an idea to an audio effect that can be used by somebody? And like I mentioned before, there's kind of this is all kind of underpinned by this idea of how can audio effects be different in the future, which is something we're really interested in answering. And so to look at this first question of why I use audio effects, I think this is probably obvious to many as well, but it's just that we want to manipulate sound in some way. And you could obviously manipulate sound without audio effects. Like, for example, if you're making a recording, you could move your microphone further or closer to the source. You could change the microphone you're using, right? But you're somewhat limited, right, in that paradigm of how you can manipulate sound. And like using these audio effects as a way to give us more power. And a way I think about that is that it's a way to expand the creator's agency, right, about how things sound. And this can be super powerful. And I think it's become super important in modern music production specifically. And it's specifically important because of these reasons, right? Like to add interest or kind of to create virtual sonic experiences that couldn't exist in the real world otherwise. And audio effects really have facilitated that a lot. And it all kind of revolves around timbre, right? Which has become increasingly important, I think, in modern music production as well, as I mentioned. But given that we know we want to create audio effects and we know what we want them to do, there's then this reality of, well, how do we build those? And the kind of existing paradigm today looks something like this, where we take knowledge from signal processing, mathematics, and others, right? And we combine that with some tools and knowledge of programming like C++. And then we have some expert user that in their head understands both of these concepts, right? And today, with that together, they can kind of come up with some idea that would enable them to define some set of instructions that defines the operation of some mathematical functions that produces some sort of interesting manipulation. And that produces some audio effect, right? And that audio effect might expose controls to the user, as I said before. But what's interesting is that you can actually think of this process, and the way that I think of it is as a search process, which is that this expert is actually searching among some space of all possible audio effects, right? And they're kind of selecting parts of that space in which they think are going to produce interesting effects. And so things like EQs and compressors are kind of parts of that space of manipulation that have kind of been obviously interesting from the beginning. And I think the big limitation here, though, is that you need to have a really deep understanding of all of these concepts in order to actually proceed, right? And it means that it cuts out a lot of people from the design process. And it also means that it may be really inefficient to search the space of possible interesting audio effects in this way. And we'll see this idea come up again towards the end of the talk about how we might address that. And so, yeah, I think this also kind of ties in with what the effects of the future might look like. And one big question I like to ask a lot is, you know, is the future of audio effects just permutations of compressors, equalizers, wave shapers, et cetera, you know, that we have today? Is it just permutations of those? Or is there something else that we haven't yet discovered, or useful ways of thinking and organizing signal processing for audio engineering? And I think this is probably not the final frontier. I think there is more out there, but it's actually difficult to figure out what that is and how it might be beneficial to us. But I think the main claim of my talk today is the fact that neural audio effects will enable this. Potentially, one method of enabling this through data-driven design of audio effects. So instead of designing explicitly by coming up with a signal processing algorithm or writing some code, you can actually use data to define this process of creating an audio effect. And that'll become more clear how you would do that as we go through the talk. So that kind of summarizes all of the high-level stuff I wanted to talk about. And now we can kind of start talking about some of the details of how we might achieve some of these things. And I want to kind of give some background on what's been done by some work in our lab and other labs in using neural audio effects, specifically in the context of analog modeling. So the way that this normally works, as I've kind of shown on this very crude diagram, is that you first start with some data set of recordings, could be any kind of recordings really, and you play them through some audio effect, and you get some output, and then you play that same recording through a neural network, and you get some output of that neural network. And right, our goal is that the neural network output should be as close as possible to the output of the real device. And so the way we achieve this is that we measure the difference between the input and the output of these, or the outputs of these boxes, using something called a loss function, which is just a distance measurement essentially. So minimize the distance between the outputs of these boxes. And doing that, we can use backpropagation, which is like a traditional machine learning approach, to update the behavior of what's inside this box, so it gets closer and closer to the real effect. And I think this basic setup should be pretty clear, assuming that we have a good way to build this neural network and to train it. And so I think there's definitely, you know, a non-obvious question of how you build this. And again, we can kind of go back to this idea at the top level that essentially it's just a box. The neural network is just a box where you put audio in and get audio out. And we can kind of model that slightly more formally just by determining that this box is composed of a few things, mostly that it's composed of some function, and that function takes as input two parameters. One, it takes as input the audio, but it also takes as input this variable theta, which is actually a vector or matrix of parameters. And essentially that simply defines what happens when you put audio into the box. How does it change the audio? And the operations are kind of parameterized operations, which means they're fixed, but they're kind of a function of this theta. So what happens during learning is that we're actually trying to find this theta such that the y at the output of this box matches what the real analog audio effect was doing. And in general, the way that this works in kind of modern deep learning is that we actually don't just have one function here, but we actually take the same function and we copy it many times. And essentially feed the output of one of these functions to the next function and so on. Basically a composition of functions, as I've kind of shown here. And the only difference is that while each box kind of does the same operations, for example, like apply a filter or apply a nonlinearity, the difference is that each layer can have a different set of parameters or theta values, and which can all be learned separately. And it's not super important how that happens, but that's just kind of the general idea of what I want you to think about when thinking about how these neural networks are built. And again, I don't want to go into too many details here, but just to give you some more high-level intuition about this, there's kind of two predominant approaches of building those functions F that I was describing. And one of them is based on convolution, which are these TCNs, and one that's based on recurrent networks, which are called RNNs. And they can kind of be broken down into these blocks, which are then stacked together, and they're kind of also called layers. And they're made up of very simple components. So in the TCN, we have something which is a one-dimensional convolution, also like an FIR filter, that then goes into a nonlinearity, which we also call an activation function. And then we might have some normalization function, which is not super critical, but it's often there. And again, the idea here is that it's actually the learnable parameters I was talking about, this theta, are actually contained within inside this conv1D, as it's often called, which is actually a multi-input, multi-output FIR filter, which is a really interesting connection to signal processing, right? That inside this neural network is actually just many giant FIR filters. In the case of RNNs, it's actually very similar, except the learnable parameters are in this RNN block. And we have the same exact activation function, but we can actually think of the RNN as something like an IIR filter. And again, the coefficients of that IIR are actually just this theta values that I was describing. And so you'll need to go into a lot more detail to understand how all these work in practice, but I kind of just want to set up this high level, as it will become useful in what I want to discuss coming soon. And I think if it's not clear already, there's some clear connections to signal processing in those two frameworks that I discussed. So we can kind of think of like the simplest distortion model as just a gain followed by some nonlinear wave shaper, right? And that could be something like a soft clipper or also a hard clipper, right? And that's exactly what this function of the nonlinearity is that I've shown here. And you can kind of change the gain of the input signal, and this will change the quality of the distortion that you get in kind of the simplest model. We can kind of imagine a more sophisticated distortion model that we might implement in DSP, where we add these like pre and post emphasis filters with a nonlinearity in the center. And again, you can build a lot of interesting distortion circuits with just this kind of super simple idea. But what's interesting is that to me, there's a clear connection between the structure of these and like the building blocks of a lot of neural networks that are used for audio, which you can see is that, in the nonlinearity filter of the distortion model, we kind of have this idea of a learnable FIR filter followed by nonlinearity, which are kind of composed in multiple layers. And so this, to me, actually looks very similar to a distortion model. And it should come as no surprise then that these networks are actually really good at modeling distortion effects, which is what they've been used mostly for in the literature. And so to kind of set up some of that, we can kind of, here's just a brief overview of some of the recent papers in the research field of people looking at using neural networks for analog audio effect modeling. As you can see, a lot of the focus has been on distortion-based effects or guitar amplifiers, and some work on dynamic range compressors as well. And the main idea that I wanted to just demonstrate with the slide, again, this is not an exhaustive list of all of the work, it's just to say that there's been a lot of success in applying exactly what I described to building these analog emulations. But again, I want to kind of move into the second part of the talk here, where we're going to then ask the question, well, isn't the whole point of what I'm discussing, how do we make a new effect? And emulating existing effects is really useful, but doesn't really necessarily help us build new effects. And so that kind of brings me to this next part of, well, actually some of our understandings of how analog emulation works might actually give us insights into how to build novel audio effects. And so that's what I want to discuss about now. So the way I actually started thinking about this is this realization that, for example, two different papers that were using the same architecture for modeling two different effects were both successful in modeling their respective effects. So for example, we can take some neural network, this F again that I was talking about, and kind of assume that it's fixed between these two different effects. So we use the exact same neural network. But then what we can do is kind of train those networks on different data sets. So one, we train on a data set of audio that comes from a tube screamer, for example, and we would then get some theta t, which is just a big vector of parameters that describes this neural network. And we could do the same process training with a data set coming from the LA2A compressor, which would give us some theta L that is a different value of, a different vector of thetas that represent this behavior of that device. And what this then, realized to me is that, we can have multiple effects that are modeled by the same architecture, where the thing that changes between them is the weights or this parameter value. And that's super interesting because it means that there exists some concept of the neural audio effect space. And in this case, I define it as simply some n-dimensional space where n is the number of parameters or coefficients, if you will, inside the neural network. And therefore, you can kind of you can think of this space here. I've just shown it in 2D for simplicity, but it would be some n-dimensional space. And you can imagine that theta t, for example, lives somewhere in this space. And also theta L lives somewhere else in this space. And then you can imagine that every point in this n-dimensional space is a different neural network with the same architecture that produces some different input-output mapping of the audio. And so you could ask, well, what if we just sample one of these other points? What will that sound like? And this was the initial idea for some of our early work in this area, where we kind of just asked the question, well, to design a new effect, what if we just sample theta randomly? So normally we find theta by training it with some data set of existing audio effect. But what if we simply just randomly sample that theta and see what it sounds like? And the result of that was that we got a super interesting set of audio effects. Some that sounded like reverb, some that sounded like delay, some that sounded like distortion, which we kind of discuss in this recent paper now about 2 years ago. And so I just want to play a quick short example of what some of those sound effects sounded like. So again, you're going to hear audio first with no effect applied, then with the effect applied, in which the only effect you're hearing is a neural network that's never been trained, and it just has random values set for the weights.
Time. Oh, time to be okay.
So hopefully you could hear in those demos. It might be hard to hear over Zoom, but I encourage you to check out the paper and more audio examples that we have online for this if you're interested. But you should have been able to hear that they were kind of these like weird effects that were added. And again, this was amazing to us because we never trained this network on any sort of audio or anything about audio effects. We just randomly generated these neural networks to get those results. And it was so interesting that I actually built a VST plugin that implemented this exact idea, so that you could actually have this VST that inside it is some neural network in which you would change these parameters in the UI that would actually change the architecture of that neural network and randomly sample the weights, and you could listen to what the audio sounded like. And there is code available for this, but it's a little bit buggy, so be warned if you want to try it out. But we could get some super interesting results with this kind of approach. And so to kind of summarize the insights from this project, essentially we found that these TCNs, or temporal convolutional networks with random weights, produced interesting effects, even though we never trained them. I think that was kind of counterintuitive. But the other thing is that we found that there was a clear correspondence between how we built the architecture, how the F was defined, that corresponded with the audio effects. So for example, making the network deeper with more layers meant that we would get effects that sounded more like a reverb. And if we kind of increased the dilations, which is another parameter of the network, that gave us something that sounded more like delay-like sounds. And shorter, shallower networks with fewer layers sounded more like distortion. And so that was all really interesting as well. And it made some sense why that was the case. But I think the major limitation of this work was that finding those like interesting effects I was just showing you was kind of like a trial and error process of just pressing a button and seeing what the random effect was and throwing it away if it was no good, or keeping it if it was interesting. And so it clearly is not like an actual usable method for designing audio effects. So what that motivated for us was this question of, how do we better search this space that I introduced? We know that there are some effects that are interesting in this space, but finding them is quite difficult. And so for that, we introduced last year a new method for kind of what we call steerable discovery, which kind of sits on the other end of the spectrum. Instead of totally random effects, we actually kind of steer the process where the user provides some input and output recording of an effect that they already like, or that they want to use to guide the process. So I have another quick short video here that will show how that works and demo and give you some sound examples of what this new approach was able to achieve.
Up in my head, oh, you're up in my head, oh, you're up in my head for good. Up in my head, oh, you're up in my head for good. And if it's for good.
Great. So hopefully that made it a little bit, give you a little bit of an idea of the results of this kind of this method. So like we kind of actually were steering the process by showing it some examples, but a very small example. And then we're able to actually create new versions of that effect that were never seen during training. Like for example, the example of making the reverb sound like a bigger room or a smaller room than the reverb we trained with. And so I just kind of want to go over again really briefly how this approach works. And it starts with the user providing some steering signals that they generate, which means just taking any audio file you have, playing it through some effect that you already like or that you want to build something similar to. So for example, a dynamic range compressor or a reverb, and getting some processed version of that recording. And then what we do is the steering process, which is actually the training of the weights, or you could also think of it as the search process. And we take that unprocessed recording, pass it through our neural network. In this case, we were using just standard TCN, essentially the exact same neural networks we were using for modeling compressors and distortion pedals. And this model also has some control parameters to it. And what we would do is just set those control parameters to be 0. And we would never change them during training, and we would never use them during the training process. And we would train this model to just copy exactly the effect that had been added by our steering signal. And we would then just use backpropagation again to update the weights of this, the theta essentially of this model to make it closer and closer to that version. And you could think of this in some way as like overfitting the model to a single example, because normally you'd have a data set of thousands of recordings from this audio effect. In this case, you'd use just a very short recording, like 10 seconds in length. And then what we found is that after we trained this model, we could actually take a totally different recording that the model had never seen before, run it through that network, and actually change these control parameters that, again, were never trained. And it would actually provide interesting perceptual controls over the effect. And that kind of corresponded to what we kind of called implicit perceptual controls, which is that we would create a model with 2 dimensions. So that's what you're seeing, like, so 2 knobs, and you would see, that's what we're seeing on these graphs here. And what I did to generate this graph is simply take some other audio file and run it through our neural audio effect, but change the value of the knobs for every space in a 2D grid. So like every combination of the 2 knobs, basically. And then what I did for each of those models is measure some aspect of the output audio. In this case, I measured the loudness for a dynamic range compressor model. And then in this case, I measured the T60 for a reverb model. So essentially the decay time. And what we found is that there was like a super clear structure that emerged in this parameter control space that corresponded with these perceptual attributes. So for example, it meant here that changing the knobs in a certain way of our compressor model actually resulted in, you know, a interpretable way to change the amount of compression that was being applied. Again, even though the model was never trained on different levels of compression. And the other aspect in the reverb case was that changing those knobs resulted in changing the size of the reverb more or less, which was a super interesting and kind of unexpected result, which let us kind of create an experiment with increasingly weird and different effects that wouldn't have been possible kind of in a traditional method of designing effects. So to summarize the results from this side of the project, essentially we found, which I think was surprising, was that we could create a very crude emulation of some effect with just a single recording. And again, our goal here is different from the kind of normal analog modeling. We don't want to emulate the effect perfectly. We actually want to create a new effect that's somewhat similar but different from the real effect. And this approach worked for that. And we found that modulating the gain of the DC offset, which is essentially how we build those control parameters of those intermediate layers of the network, is actually what gave us these variations of the effect, essentially like controls that would actually help us change the effect, even though it never had been trained on it. And I think for me, from a high level, the biggest takeaway from this approach is that, this kind of steerable discovery method provides a route to designing new audio effects without any programming or DSP knowledge, right? Because in our system, a user can supply just an input and output recording, and they can build some new effect and kind of experiment with it and change, and maybe change those recordings, for example, and see how the effect of the design changes in correspondence to it without having to like go into C++ and understand all of DSP in order to do that. I'm not saying that these DSP and programming are not important tools. It's just that this is another way of thinking about how we might design audio effects. And as I kind of start to get towards the end of my talk and wrap up some of the ideas, I want to note that like all of the work I discussed is very new and it's still in its very early stages. And there's a lot of open questions that we still have in the research field that I also would want to encourage those of you listening to think about and potentially work on if you're interested in this area of research. So I think if it's not clear by now, like this idea of searching the space of audio effects is something I'm really interested in. And I think it's an important way to think about audio effect design. And in this kind of Venn diagram at the bottom is kind of how I envision it. And I acknowledge that this Venn diagram may have some inaccuracies, but I think it captures some of the ideas that I'm trying to portray. Which is that we can kind of imagine that, there's this green circle here that kind of includes all of the existing DSP plugins that we have today, right? And then there's some other space of effects, of neural audio effects that can exist. So for example, some of the effects that we've designed that, are not available in existing plugins that produce interesting results. And then there's kind of this crossover, which is all the neural audio effects that emulate existing effects, for example, would kind of live in this space. But even beyond this, I think is really interesting, is this kind of the blue space, which is all possible effects, even effects that can't be modeled or produced by our neural audio effect approaches, and how we achieve those and how we, if that exists and how we may build it is a super interesting problem for future work. And yeah, so like I was saying, this audio effect design as a search problem, I think is an interesting way to look at audio effect design. I think a big question and a current lack of our own work that I want to point out is that, we don't even have a method for determining if an effect is novel or not, for example. So how do you know if you just copied something that already existed or whether or not you're actually making something new? And I think this is an area for future research to build evaluation metrics for this kind of question. And related to that, I think there's also a very interesting human aspect to this question, which is there's clearly some relation between an audio effect, which is just a box that produces some manipulation, and how we perceive that, what that box does, right? And some of those boxes do more interesting things to our ears than others do. And building a model building a computer model that could answer that question of, given two effects, which one is more interesting, would be a super powerful way of doing the search process, because you could kind of create random effects, show them to the system that had learned what is an interesting effect, and then actually kind of like traverse this space to find the interesting ones. Again, there's kind of almost no literature on this question so far, and I think it's a super interesting area for future research. And I think even beyond our talk of neural audio effects, there's kind of this general question of, do audio effect classes exist beyond kind of our current DSP definitions of audio effects, like filters, buffers, and things like this, and dynamic range compressors, gain controls? Like, is there some actual way of thinking about audio effects that go beyond these definitions that would let us create different, ways to structure this processing that would create interesting manipulations? Or have we kind of discovered it all? And I'm kind of the belief that we haven't discovered it all, because that seems kind of less likely to me. But I still think this is an interesting thing that not enough people are talking about, in my opinion. And I think beyond those kind of philosophical questions, there's a lot of interesting practical implementation questions that are open. And I think these might be of particular interest to our audience today as well. And I think one of the biggest challenges here is that current approaches are not proficient at modeling all different types of effects. I think we've kind of shown that these models work for these effects, but they have kind of all these shortcomings. And essentially designing generalized architectures in the neural network space would be super powerful for this. And there's already been some great work from another PhD from our lab in the past, Marco Martinez, who looked a lot at this question. But I still think there's some open ends there that need to be tied up. I think the other big thing that we found is that interesting effects that run in real time are very difficult to find. Essentially, like the more interesting effects tend to require bigger neural networks, more compute, and all of this stuff, which makes it really difficult for audio engineers to use them in practice because they need to be able to put them in a DAW, for example, and run them. So I think more efficient architectures is a clear question that needs to be answered here. But there's also this problem that even with efficient architectures, there's even just kind of a practical problem of the engineering barrier of like, I have a neural network and I've trained it in Python using PyTorch or TensorFlow. How do I actually get that to run in my plugin? Is actually a really big challenge for anyone knows that's tried it. And there's not really good frameworks or tools for doing this. And so I kind of think we will see in the coming years, and we're already starting to see it now, kind of improved frameworks for exactly this kind of question, which I will hope accelerate this research in this area. So as I wrap up, finally here, I kind of just want to again summarize the main takeaway points from this talk that I hope I made clear and maybe convinced you are interesting. The first is that neural audio effects provide a new method for designing audio effects, which can kind of be seen as like a top-down approach versus a bottom-up approach using data. Because like a bottom-up approach would be like understanding each DSP block and then putting those together to build some effect. But the bottom-down approach, the top-down approach is like this neural network idea. You just build a giant system that's very complex and chaotic, and you actually adjust the weights or search its parameter space in order to find some effect that's interesting, even though you don't understand how the individual elements are working. I think we've also shown that like this searching of the weight space is one method, but not the only to design neural audio effects. And like I mentioned before, I think that this is interesting because it also doesn't require DSP or programming, explicitly in order to use this approach to look for interesting sounds, which is not something that was really accessible to people in the current paradigm. And again, as I mentioned, there's many open challenges and lots of opportunity to advance the field here. And before I close, I just want to give a brief shout out to a few different resources and things that are available for people that are interested in learning more about this research. All of the code from the projects I discussed today from our lab are all open source, so you can find them on GitHub. There's also Colab notebooks online, so you can actually like run audio through these models in the browser, train your own models in the browser for these different applications, which I encourage you to check out if you're interested. There's also some other projects, not from our group, from other great researchers and people working in this area. One is this GuitarML project, which maybe is one of the best open source projects around neural audio effects that's really accessible. Essentially, they have some Juice plugin that you can run different pre-trained neural networks in there, guitar models and things like that. And you can actually people are sharing different models and you can build your own and share them with others and put them in that plugin, which I think is a super cool initiative. Most recently, there's also been this Neutone SDK that's been proposed from a really interesting group. And essentially, they built an SDK that lets you wrap PyTorch code into a VST plugin that can then run in your DAW. And you can also easily share audio effects or neural network audio effects between different users without having to deal with all of the C++ compilation problems that you have when you want to put a neural network in a Juice plugin for yourself. And so I'm really excited for seeing as this develops, how it can help accelerate bringing in these neural audio effects into production contexts. And if you're interested in the lower level details, there's also this great library, RTNeural, that is all written in C++. And it's basically a backend for converting PyTorch and TensorFlow models into C++ code that can easily be put into a Juice plugin. And so I think this is a great initiative to try to make it open source and easy to build plugins. And yeah, so that wraps up everything I wanted to talk about today. Hopefully you found some of this interesting. I just also want to give a shout out to my PhD supervisor, who's Josh Rice at Queen Mary. And he's kind of been a leader in a lot of this work in intelligent audio engineering. And it's been super helpful in all of this work. I also want to kind of give a shout out to the Center for Digital Music, which is a great department here in London. And we also have a PhD program, which I'm a part of, this AI and music PhD, that's accepting new applicants every year. So if you're interested in doing research like this in a PhD, I'm more than happy to talk to you about it. And we're also always open to collaborations, whether you're a researcher or a programmer or a developer or anything. So if any of this is interesting to you and you think you might have some ideas here, I'd love to talk to you about it. My email is there, and you can follow me on Twitter as well if you want some more updates of our research. But yeah, thanks so much. That concludes everything I wanted to talk about.
Great. Thank you very much, Christian, for that awesome presentation. And the live chat has been really busy with chatter and questions, and we have loads for you. So first question comes from George, and he says, hey, Christian, do you think neural audio effects will come mostly from established companies like Native Instruments or newcomers like Tons AI?
Yeah, it's a great question. I mean, I obviously can't say for certain, but my feeling is that it's the small companies that will lead this more so than the big companies, just because the big companies are trying to serve, their existing user base and build tools that help people today. And it's not to say that neural audio effects don't help people today, but they're definitely more exploratory in nature. And I think we're going to need someone that takes a big risk on this idea in order to see it through. But I do think there's going to be a big breakthrough in this area.
Right. Next question is also from George. Where do you see GPU processing in this area? So if you've seen GPU audio, they've come out with a really compelling offering recently.
Yeah. Definitely. I mean, I think that's a key question. And I wonder, I've talked to them a little bit at GPU Audio about this exact thing, because it's something the researchers are interested in seeing, how that workflow could exist. I think if there was just press a button and it ran on GPU for a VST plugin, everyone would love it. I'm still skeptical of how easy it's going to be to make that happen between the existing machine learning workflow. But I think that will be helpful. But I also am worried that it's not like a one size fits all solution, because many people are not going to have a GPU or kind of hardware to run that. And so having some ability to fall back to CPU is still probably going to be necessary for the long term.
Nat Poe asks, how did you model the nonlinearity, and was it learnable as well?
Yeah, so there's a lot you can do with the nonlinearities. In general, in most machine learning approaches, you kind of just pick a fixed nonlinearity, so just a fixed wave shaping function, and you actually you kind of assume that does enough, and you actually just let the filter kind of modulate the signal going into that nonlinearity to get all the interesting behavior. That being said, there are some approaches like our own that actually learns part of the wave shaper, and you get some small benefit. But I would argue that all of those are kind of technical details that aren't required for success of the approach.
Nat Poe also asks, how many layers of 1D convolution and non-linearity did you use?
Yeah, it's a good question. And I think it's, again, context dependent. So for some of the models, we use very few, some of them we use a lot. So that means it can range everywhere from, I would say, 3 to 20 layers, depending on the network architecture. So it's kind of just very context dependent.
Okay. What were some of the qualities associated with changing convolution width or the activation function?
Yeah, so I didn't get to discuss that a lot in this talk, but we discussed it a lot in the paper for the randomized overdrive neural network. So I encourage you to check that out if you want further discussion on it. But just to kind of summarize quickly, there were really clear differences in how the activation function changed things, again, basically changing the wave shaper. So using things like kind of a smooth wave shaper sounds way different than a hard clipping one, which we would kind of expect. It adds a lot more harmonics that sound a lot different. But what was interesting is that we kind of, inside that plugin that I built, used like a range of 10 different activation functions or wave shapers that you could think of them that are kind of like the common ones that are used in machine learning, but are not commonly used in the audio world. Because for example, they like only have a positive signal and everything below negative gets turned to 0, for example, which in the audio domain would be like, well, that's weird and doesn't sound good. But we found that it actually produced interesting effects when you stacked them a lot. And I think that's kind of interesting too, because again, you could actually just look at these like TCN networks as basically multiple layer wave shapers, like something like Isotope Trash, like, right, like lets you build kind of like stack wave shapers. It's actually very similar to that conceptually. And the idea is that I think the problem is that we never, in those ideas of building wave shapers, we generally don't like stack 10 of them or 20 of them in order, because it just becomes so chaotic to understand it. And the interesting thing is that using it in the neural network paradigm, we can actually do that. And it works because we kind of train it to work in some sense. And that kind of let this kind of sound effects come out that weren't apparent in previous approaches.
Right. One more question from Nikolay Glazerin. Is it hard for a professional producer to recreate the same configuration of knobs on a delay effect after listening to a record? Is neural audio effects currently directed more towards amateur producers, people who may not code at the moment?
So I would argue that that's something a little bit different than what I discussed today, but it's actually something that is like comprises the other 60% of my PhD, which is like learning to control audio effects essentially. So like assuming you have some fixed chain of effects in a DAW and you get some example sound, how can I like have a neural network that figures out how to set those knobs back to what they were when that recording was made? Or for example, the recording comes from a totally different source and you want to make them sound as similar as possible. And that's kind of actually what this differentiable signal processing is about that I mentioned, but didn't talk about in depth. But to answer your question more specifically, I would argue that the neural audio effects are actually at this point more geared towards kind of the expert audio explorers, like people that want to explore with neural networks and audio engineering. And I even have one song that I mixed using only neural audio effects and no other effects in the DAW that I didn't have time to share today, but I can also point you to that, which again is trying to just demonstrate that this is like an interesting and exploratory area, but not so much an area that I would encourage amateurs to get into, because they probably still need to understand all of the basic audio engineering concepts.
Great. That's it for questions. Thank you very much, Christian. That was really awesome.
Thanks so much for having me.